finish this chapter. Remember, we are chapter number 6, Hawking radiation. And we have been discussing this for a while. This is the 6th class on this, and we could keep going for longer, but we have to finish at some point. So the last thing I wanted to discuss is section 4, which is what's called consequences. I described the first one, which is black hole thermodynamics. And as I have said before, I cannot emphasize strongly enough how important is that, how conceptually deep that connection is, and how really Hawking derivation clarified many things. And another of the important consequences, there are others, but I have chosen these two, is what we call the information loss paradox. And I bet that you can already imagine what is going to happen and why it's going to happen, because in the Unruh effect, something quite similar happened. But there, the resolution was much clearer. Here is not that clear, and people have been discussing that for 4 years. But there is no still agreement on what is going on. So this is highly non-trivial. I'm going just to summarize it. What is the main problem, and what are the main proposals to solve it? And just tell you that this is work in progress, and people consider that this is one of the most important open questions in gravity and quantum mechanics. So remember, Hawking tell us that Hawking computation. Let me emphasize that was done using a fixed black hole spacetime. Remember, all this course, what we are doing is quantum fields in a given spacetime. So the black hole spacetime was fixed, was given for us. And when we do that, when we put a quantum field on that, what Hawking told us is that a flux of energy, positive energy, reaches straight plus, and at the same time a flux of negative energy crosses the horizon. So remember, we have the black hole diagram. Hawking tells us that if the initial state is the vacuum at early times, then at late times, much after the collapse has produced, at very late times there is a flux of thermal radiation here, and there is an ingoing flux of negative energy. This is positive energy going inside the horizon. First of all, you may be surprised that energy is negative, but remember, in quantum field theory, energy can be negative. Think about the Casimir effect, where you have the vacuum energy of the electromagnetic field between two conducting plates. You compute the energy is negative, and this is what produces the Casimir force. So in quantum field theory, negative energy appears everywhere. If we had in the chapter of renormalization and the energy momentum tensor, one can see why is that. But that is later on. I haven't computed these fluxes for you. I am just telling you that is the case. In order to compute that, what you have to do is to compute the energy momentum tensor in the in vacuum, which is the vacuum, the state in which the field is. Remember, we work in the Heisenberg picture. The state is fixed once for all. So you compute that. This is a function of the point. You evaluate it there, or you evaluate it there, and you can see it's positive or negative. That computation is highly non-trivial. First of all, because as I said, to compute that, you need to know the solutions to the plane coordinate equation in the whole geometry, and we don't have analytical solutions for that. So as far as I know, there is no single analytical computation of the energy momentum tensor in 4 dimensions. There are numerical computations, and there are also analytical computations in simplified models. For instance, in 2 dimensions, if you suppress the angular dimensions, then you can do it analytically and you can see these negative and positive flags. But in 4 dimensions, we don't have any analytical computation. But numerical analysis tells us that this really happens. And there are other many arguments why that must be the case. But just to let you know that I haven't derived that for you. So because we have these negative energy flags, now, if we go beyond this fixed background, now, if one considers semi-classical Einstein equations, remember I mentioned them at the very beginning of the course. 8 by G, which is cut 8 by G. So that means that if we now go beyond our approximation, that assuming that the space-time is fixed, and you put that here, that energy momentum tensor, what we expect is that the black hole is going to lose mass through Hawking radiation. I haven't done this computation either, and in fact, solving these semi-classical Einstein equations are even more difficult than getting the energy momentum tensor. And for them, you need the energy momentum tensor. So all what people have done are simplified models to see that. But the conceptual picture is that, assuming the background fixed, you see that there is a negative flags and a positive flags. And therefore, if we believe these equations, which, at the horizon or outside of the horizon, there is no reason to not believe them, just because, remember, the space-time curvature at the horizon can be as low as you want. So there is no reason to doubt about some of these equations. The conclusions are that the black hole mass evaporates. Lose mass and eventually evaporate. And I emphasize that this is an extrapolation of our computations. Nobody has really computed that. But there is no reason to believe that this is not true, in particular at the beginning of the evaporation. Once the black hole gets to the Planck mass, then this will not be true, and we don't know what happens. But this should be, there is no reason to this not be true at the beginning of the evaporation. And this is what we call black hole evaporations. And remember, the first paper by Hawking was called black hole explosions, because he was thinking that the black holes evaporate, they get hotter and hotter when the black hole evaporates, and finally, the final burst will be like an explosion. And in particular, Hawking drew the Penrose diagram of this situation, the Penrose diagram of an evaporating black hole, and was something like that. So this is the Penrose diagram. This is the singularity at r equals 0. Also r equals 0 here. The event horizon here. And what we have, initially we have a collapsing star, forms a black hole. The black hole emits radiation. Hawking radiation gets here to Scrape glass. But after some time, the black hole has evaporated completely, and in this region, we have just Minkowski spacetime again. So this region, this shadow region, is like Minkowski because the black hole has evaporated completely. All the energy of the black hole is in sky glass. So this is the Penrose diagram that Hawking drew of an evaporating black hole, and on this diagram is where this information loss paradox arises. So here in sky glass we have Hawking radiation, and after time always goes vertically. So after some time, the black hole has just completely disappeared. Is that okay? So it's important that you understand this diagram because all what I'm going to say is based on it.
Okay, but this is not correct. Right?
Sorry?
Having black hole reaches at Planck scale.
And this is an extrapolation, right? There is some assumption here. But the assumption is really very implicit, and this is the diagram that people consider to discuss the information loss paradox. So there is no question about that. I have questions about that. But in general, this is the basis of the information loss paradox. I will go over that.
It seems strange to me that there's a sudden disconnect, either at black hole formation or at black hole evaporation between Minkowski space-time and short-shell space-time.
Say it again.
It seems strange to me that there's a sudden jump between the two space-times. Is it really sudden, or is
no? It's not sudden. That seems here, but imagine that the black hole is someplace and it's evaporating. The mass is reducing. That mass goes to infinity. The black hole is shrinking, and eventually all the energy will be.
Right, but is the metric really discontinuous
No,
like
it's not
that?
discontinuous. No.
Okay.
It's just like a star which is losing mass by radiation until completely radiates out.
Okay.
After some time, that radiation will reach infinity, and you will get just nothing inside. So the black hole has completely disappeared. This is what you have. Of course, all that details you cannot see them here. But that is the picture. You have a black hole initially. It has been produced by a star, and after some time, Hawking evaporation. But this, and I emphasize this because I talk about this Penrose diagram, complete evaporation poses a problem. The black hole has completely evaporated, that is not there anymore. We don't have black hole anymore. So all correlations or entanglement between Hawking Wanda reaching sky glass and Wanda falling inside the black hole remember, the picture here was that, let me just draw this line. The initial in vacuum in sky minus was full of correlations. The 2-point function was non-zero, but there were correlations between this point and this point. But this corresponds to mode function that escape to infinity, Hawking radiation, and these two mode functions that go to the singularity. So we realize that that these two guys are 100% correlated, and this is why this pure state looks like a mixed state here. Each Hawking quanta is correlated precisely with one quanta going inside the horizon. If you don't remember that the in vacuum when written in the out int Fock space was exponential of out int acting on the vacuum. look at your notes, sum for all n, etc., for all quantum numbers, etc. So remember we wrote this as sum, essentially sum over number of quanta, n quanta out, n quanta in, sum over all with quantum numbers ln, etc. So, but we were emphasizing that the state here is mixed because all correlations between mod C and mod C are not accessible to straight class. So, if the black hole completely evaporates, those correlations are lost. And you reach to the future, there is no black hole. All correlations that went inside, they are not in our universe anymore. So all and quanta falling inside the black hole, so all correlations between Hawking quanta falling inside the black hole disappear. I don't know. 1 or 2s? 1, 2 p's? Yeah. From the universe. So a pure state at scri minus evolves to a to a mixed state at scri plus. The black hole is not there anymore. If the black hole is there, you can say that that the information, the correlations are inside the black hole. But the black hole has evaporated. It's not there anymore. There is no place where to hit the correlations. So you start from scri minus, you go to state class, pure state initially, you have a mixed state finally. So therefore, the quantum mechanical evolution from scri minus to scri class, this is what we call the S matrix in quantum field theory, evolves a pure state, the state in, to a mixed state, which is the Hawking density matrix describing a thermal state at the state class. If you know something about quantum mechanics, you will realize that this evolution is not unitary. A unitary evolution can never connect a pure state with a mixed state. So if the black hole evaporates completely, we had a pure state, entropy 0, and you get to a mixed state, large entropy, information has been lost, quantum mechanical evolution is not unitary. Remember that unitary time evolution is one of the pillars of the quantum mechanics. That time evolution is given by the unity operator, e to the I, the Hamiltonian. That is Hermitian, therefore Hamiltonian is Hermitian, therefore that operator is unitary. And unitarity has to do with probability conservation. The fact that you have an electron, you have today probability 1 of finding it, you evolve it, in the future you still have probability 1 of finding it. So all this probabilistic interpretation of quantum mechanics relies in the unitary evolution. So this seems to be violating one of the pillars of quantum field theory, of quantum mechanics in general. So seems a violation of one of the pillars of quantum mechanics. And this is a big issue. This is what we call the information loss paradox. So just to refresh your memory, recall what happened in the Unruh effect. In there, everything is static, so it's much simpler, and we didn't have any problem. In the Unruh effect, we had the right and left Riller wedges of the Minkowski spacetime. We had the Minkowski vacuum, which is a state defined everywhere. And we found that the Minkowski vacuum is made of correlations between points in the right and left with Riller wedges. The Minkowski vacuum can be written as, remember, as a sum over n of a staff with n quanta in the left Riller wedge and n quanta in the right Riller wedge. That was the Minkowski vacuum. Of course, if we trace out the information here, if we forget about what happens here, this Minkowski vacuum looks like a thermal density matrix in the right Riller wedge. And I was asking you, is that a loss of information? Of course not, because you are just looking part of the system. The information is between this guy and this guy. So there, in that situation, nobody was going to complain that we are losing information, because we are just looking a part of the Minkowski vacuum. Here, something very similar happened. We have modes out and in, modes in a straight plus and modes inside the black hole, which are correlated. If you look only at the state plus, the state look mixed, because the information is between straight plus and the interior of the black hole. But now, if the black hole evaporates, we don't have, it's like if we suddenly this region evaporates from the spacetime. So if something happens here and this region evaporates from the spacetime, it's not there anymore, then we have lost those correlations. This is what happens in the case of the black hole. The correlations were between straight plus and the interior of the black hole. But if the black hole evaporates, those correlations are gone from our spacetime.
So it's the probability of the Hawking radiation that wouldn't be conserved, right?
Say it again.
What probability isn't conserved?
Probabilities in the quantum theory, they have to do with the no, of course, when I talk about probabilities, you are thinking of quantum mechanics, when you have a particle and you have probability of something. Here, and remember that mathematically the probability has to do with the norm of the wave function. You have a wave function, you compute the norm, which is this times this integrated, and this gives you probabilities. In the quantum field theory is very similar. You have a state, and this norm is conserved. So in quantum mechanics, if you evolve this with time, the norm is conserved. And this is what we mean by that in the Schrödinger theory, probabilities are conserved. In the quantum field theory, you have a state, and probabilities of different things have to do with the norm of that state. And we know how to compute it, because we know how to compute, how to write this in terms of states with a different definite number of particles, and we know how to take inner product. But if the evolution, if the evolution is unitary, this state is going to evolve to this state. This is if the evolution is unitary. If you compute the norm of this state, you have to take, this. And this is just the conjugate of this one.
Right.
And if it's unitary, this is 1, this is the probability is conserved.
Right.
But if U is not unitary, then probabilities are not conserved. The norm will not be equal after time evolution. So any probability you want to compute, any question you want to ask about probabilities will not be conserved.
So if you look at that from a frequentist perspective,
From a what?
frequentist of statistics perspective, does that mean that a repetition of experiments with time as the black hole evaporates actually changes?
I don't know if I will study it in that way. So
Here,
so this is what it means, and mathematically, pure state goes to a mixed state, and that is just forbidden in quantum mechanics. Quantum mechanics, if you have a unitary operator, a pure state goes always to this state, and that is pure by inspection.
Are we just saying time evolution is not a unitary operation anymore?
This is what it seems to be happening. That this evolution cannot be given by a unitary operator. We have in the past a pure state, in the future, because the black hole is gone, we look at it, it's a mixed state. So what we call the S matrix, which is precisely the unitary operator relating the past and the future, cannot be unitary.
Okay, here we are talking about quanta, right? Like in Hawking radiation, there is quanta, and those are correlated with the quanta falling inside black hole. But when black hole evaporates, those quantas won't be lost, right? I mean, like those will come back to the I plus. I mean,
No, whatever happens, whatever goes inside the horizon is lost forever. Inside the horizon is lost forever.
but like after, I mean, evaporation means like those come back, right? Like I mean, it
That's
is
the
losing.
No,
That's
no.
the quanta reaching I plus. We're talking about the negative energy quanta
Right,
never
so-
leave the black hole.
So
that would
you have
reform the black
in
hole.
straight minus, imagine that they compute the two-point function in
Yeah.
straight minus in the in vacuum. Between this point and this point,
Yeah.
they are separated by the extension of the horizon. The correlations are non-zero. And in fact, this is why the in is a pure state, because it's full of correlations, and it makes a pure state. But now, take the quanta associated with that, the quanta, what I mean is the mode functions, now in the in-out representation. One of them will go to a straight class.
Yeah.
The other will go inside the black hole.
Yeah.
This straight class is what is going to become Hawking radiation later on.
Yeah.
But this guy is correlated with this guy, 100% correlation.
Yeah.
Cannot be correlated with any other guy because it's maximum correlation. And after the evaporation, this disappears. So we already have Hawking radiation, but all what enters inside the horizon by causality cannot reach straight class. Just by causality, anything inside the horizon, the evolution will die in the singularity. Can never reach straight class. So all those correlations here, they have been separated, and the ones here have been lost.
Okay, so what type of evaporation? I'm like, if I think like water boiling and evaporating, right? So it is in some container.
But you don't have an even horizon there, and you don't
Yeah.
have singularity there.
Okay.
So this is what happens here. That correlations one go to inside the horizon. By definition of horizon, that can never go to a straight class unless you violate causality.
Okay.
If you don't violate any rule of the game, that can never reach any more straight class. That will die in the singularity, and after the black hole disappears, there is no singularity anymore. The black hole is not there. We only have Hawking radiation at the straight class. So there is nothing else in the universe. What are the correlations? They have been lost.
Is there one field here or multiple fields?
One field, one scalar field.
So if there's one field, then there's no meaningful interpretation of probability anyway, because you can't repeat an experiment. So the time evolution operator is not really an observable, right?
But I mean, there is quantum mechanics. You can make predictions, and if after the evolution the state is mixed or is not mixed, I mean that is a prediction, and you could set it up questions to check that.
Is
So
it the case that the time of evolution 2 square plus or 2 infinity?
So you prepare a bunch of black holes, wait until they evaporate, start measuring many times.
So measure many black holes.
For instance, theoretically.
Oh, okay, I see.
Or you
Prepare
have,
multiple universes.
you have Hawking radiation. You start measuring many quanta and taking correlations, and you will see the same things. Sorry, I interrupted.
Is finite time evolution still unitary?
Finite time evolution is still unitary.
Because evolving into square plus is problematic, but
Right.
not evolving all the way to
Right.
infinity.
So if you start taking this Cauchy slide and evolve from here to here, everything is fine. From here to here, everything is fine. From here to here, I mean, let me avoid the Planck region when the curvature is Planckian, because then I cannot trust quantum field theory. But I can get as close as I want, even out of the Planckian regime, and evolution is unitary. It's only when you reach the singularity, and then you evaporate it.
Okay, I mean like at Planckian scale, I mean the complete evaporation that gives me like that. There like we have to worry about paradox.
Right, after the complete evaporation. Exactly.
Yeah, there.
This is the one.
Yeah, but if there is not complete evaporation, then we can be safe.
We can be safe in principle.
Okay.
And many people say that the black holes, evaporating black hole is a machine of destructing information. You start throwing information inside, and you only get thermal radiation. You throw an encyclopedia, you get thermal radiation. You throw a ball, you get thermal radiation. Oh, doesn't, you know, the black hole doesn't distinguish between that. So I mean, there are many subtleties, and I don't want to go over the subtleties. So let me just restrict to this. We have a pure state, and it becomes a mixed state in state class. Therefore, the time evolution from the S matrix from here to here is not unitary, and this is what people call the information loss paradox.
That transition from black hole to evaporated black hole was somewhat instant, right?
Into the full evaporation,
Yeah.
I mean, it will take a while. You know, remember I was describing
Well,
last time that the time is of the order of the Planck mass, the mass of the black hole to the cube power. Of course, here there are extrapolations because you know we cannot trust the process in the last stage of when curvature gets the Planck scale. But you know, this is the Penrose diagram that Hawking wrote, and people on that basis find a crucial incompatibility of black hole spacetime and quantum mechanics.
But we believe that unitary pseudo-result. And that is
Let me elaborate on different beliefs and different. So what I want you to understand is what is the statement of the problem. Very similar to the Unruh effect, where the Minkowski vacuum is made of correlations between left and right. But in the Unruh effect, the left side never evaporates. So it's always there, and you would say, of course, you know, the information is between here and here. Those correlations make the Minkowski vacuum a pure state. But the difference here is that the interior of the black hole evaporates and disappears from our universe. So all these correlations are gone. Just to tell you that this paradox is unresolved at the present time. So there is no agreement on what is going on. So just let me write for you a few proposals, and you can decide what you like and what you don't. I can tell you what I like.
you can.
So proposals. The first one: accept that physics, quantum mechanics in particular, is not unitary at the fundamental level. Many people believe that. Many people believe that this simple example, which is not yet quantum gravity, is just signaling that at the fundamental level, quantum mechanics is not, quantum field theory is not unitary. And I have heard many prominent people say that they strongly believe that is the case, that we have to give that unitary. But you know, then you open the box. You are changing the rules of the game, and then you have to, I don't know how to do quantum mechanics with a unitarity. You know, I have to do something else. There are other proposals which, you know, a black hole never forms. Certain, it's not a joke. It's serious. So, you know, that when the star collapses, something happens there that stops the collapse, and you get what people call fastballs, which is something that is almost like a black hole but never crosses the event horizon. So an event horizon is never forms. From outside, you could not distinguish that from a black hole because, you know, if the surface of the star is very close to the horizon, any light emitted will be infinitely redshifted, and you will never see it. So for you, from outside, it will be indistinguishable from a black hole, but a black hole never forms. Of course, you know, to do that, you need to change radically ingredients of general relativity. General relativity, black holes form. So you have to come out with new physics that tells you why that happens. Even recently, there was this famous paper that says that, you know, maybe Hawking radiation before collapsing can stop the collapse, and, you know, I don't believe that. But you know, there are many speculations about that.
I get that in general relativity, a Schwarzschild metric is a solution to that differential equation, but that's not to say black holes need to form.
Right. I mean, you can add new physics, like
But that,
some-
we don't need to change general relativity if black holes never form. We can just say they don't.
right. But you need to come out with a mechanism that stops the gravitational collapse, and we don't know any general relativity. Ideas, maybe the initial Hawking quanta energy quantum tensor stops the collapse. I think is very implausible. But people have argued many things. I'm just reporting what is in the market.
Yeah, but like what is that?
The
I
main
mean,
to
like
defend.
with other experiments and all, like in astrophysics and like this gravitational waves and all. So we have like sound belief that there exists black hole, right?
But these people could say that no, these fast balls from outside are indistinguishable from a black hole. Of course, if you see the argument, there are always new ingredients which are not in GR or in standard quantum field theory. So they are no assumptions, and you can decide if you like them or not. Speculation is free.
Yeah.
Theoretical physics is free. So normally all these proposals break our basic principles, but who knows what is reality? Is what the authors would say.
There's something called, I read a newspaper, it says eternally collapsing objects. Where somebody showed that, like in Hawking proved that in a general scenario you would have a collapse, right? Somebody changed something in that theorem and showed that it never collapses. Like some
I don't know that in particular, but there are ideas of all possible tastes. So another idea is that there is a remnant. I think this is the right word. Let me know if it's right. Is remnant with T?
You probably went MN, remnant.
Remnant. Thank you. Which is that the black hole doesn't evaporate completely, that there is some remnant there of Planck size, and all the information is there.
This looks okay.
People argue against that because then, you should be able to encode an arbitrary amount of information in an arbitrary small object. And if those objects exist, because the entropy is so huge, they will be forming almost spontaneously everywhere. And people believe that that is not a good proposal because of that. Infinite amount of entropy, because you can create a black hole with as much entropy as you want in a region, in a particle of Planck size. So the amount of degrees of freedom that must have are so huge that we should expect the spontaneous creation of those objects everywhere. And that doesn't happen.
if the area is decreasing, so wouldn't the entropy decrease, or are we?
But the correlations with the sky class are increased. I mean, I am not defending anything. I am just giving you a list of ideas in the market.
In the last class we did that area is proportional to entropy.
Right. But you also have this. We can discuss it later if you want. Otherwise,
How do you know it doesn't happen everywhere?
I was thinking.
I don't see that. And, one. Don't make me defend. So I have never said that.
No, I mean like you said, right? Like there can be horizon here also. Like,
Right, but
that is different than, and that is different.
because in particle physics we should see some processes, but our particles disappear in those kind of objects, and we don't see that. We don't see nothing similar. Firewalls. This proposal has been quite popular in recent times, and initially the proponents were just trying to argue what one should do to recover unitarity. And then they found these extreme consequences that I will tell you in a minute what they are. Most of the initial proponents, they don't really believe that this is going to happen, something like a firewall. But, maybe some believe, but the idea is that to show that, in order to recover unitarity, you will have these extreme consequences. And what do I want to say?
How much do you believe in number 4? Like how much percent? Yeah.
This is being
Right,
recorded,
a
so-
percentage.
What's a firewall? I'm confused.
I am going to explain you what a firewall is. I haven't explained it yet. So let me
Okay.
finish and then you can ask me. Of course, first of all, they believe people in the string theory, and people, the proponents are normally supporters of string theory. In a string theory, you have this ADS CFT correspondence that tells you that that gravity in anti de Sitter is dual, so it's just you can rewrite it as a conformal field theory living on the boundary of anti de Sitter. Anti de Sitter space is a space with constant curvature negative, and it has a boundary. And Maldacena made the conjecture that that gravity inside anti de Sitter is dual to a conformal field theory on the boundary, and that is extremely important conjecture, and it happens. It seems that it's quite true, even though there is no rigorous proof. But all indications are in a strong support of that. And they say, okay, but the CFT is unitary because it's a conformal field theory. So if the CFT is unitary, whatever happens inside with gravity has to be unitary. So they strongly believe that any non-unitarity is an artifact of something that we don't understand. So with that in mind, then they try to change things to make it unitary. Now let me tell you what they change. Of course, they start with this Penrose diagram, and as you indicated, one could question this Penrose diagram, and I question it. So in all proposals there are assumptions, hidden normally or implicit. So one has to be careful with any proposal. Even if the proposal that I would make, there are for sure hidden assumptions. So let me just draw it again. I mean, the details are complicated, but the idea is not complicated. As I said, if I extrapolate the horizon here, what happens is that strong correlations between points nearby, one goes to Hawking radiation, the other falls inside the black hole. So we have in quanta, out quanta, 100% correlated. And they say, okay, maybe is that something happens with Hawking radiation that is very approximately thermal, but not exactly thermal. That there are small correlations between Hawking quanta, because there are a lot of Hawking quanta. If I was able to translate the correlation between, I said that the guy 1 is correlated with the guy 2, and this is another out mode 3. If I was able to translate the correlation between 1 and 2 to 1 and 3, then the information will come out in Hawking radiation. So initially, we have correlations between 1 and 2. So the idea is maybe we can convert it to correlations between 1 and 3. If that is possible,
One is in past, right? I mean, like,
one is the one that goes to infinity,
there.
and 2 is the one that goes to the horizon.
Okay.
So if I was able to translate the correlation between 1 and 2 to 1 and 3, then the Hawking radiation will encode, maybe in a very subtle way, but will encode the initial correlations, and the state here would be a pure state. That is the idea. So convert that to correlation. If this is true, then Hawking radiation will encode the correlations. And there are many proposals of that maybe Hawking radiation really encodes, is not exactly thermal, it's very approximately thermal, but these small deviations is what generates what encodes the information. But these people just, write in a few assumptions, found that that is extremely difficult. First of all, if you go to quantum information, is this kind of monogamy of correlations that tells you that if 1 and 2 are completely correlated, 1 cannot be correlated with anybody else. This is what people call monogamy of entanglement. I repeat, if 1 and 2 are completely correlated, 100%, as happened here, then 1 cannot be correlated with anybody else. Entanglement, maximum entanglement is monogamous. You can only be maximally entangled with one other quanta, not with 2. So, in order to make 1 and 3 correlated, you have to break the correlation between 1 and 2. And the statement is that what people found is that if you break the correlations between 1 and 2, then something dramatic happens at the horizon. So let me just write it. Using quantum information arguments, in particular the monogamy of entanglement and the non-cloning theorem, people have shown that breaking the correlations, the entanglement between 1 and 2, so between the out and in quanta, make the quantum state of the field. So the in quantum state will be modified, make the quantum to have arbitrary energy at the horizon. So the statement is that if you want the correlations to come out with Hawking radiation, it is unavoidable that the quantum state is singular here. The energy of the quantum field will be infinite there. You will have a singularity. This is what people call the firewall. Firewall is just the fact that in order to take out the correlations and encode them in Hawking radiation, quantum information implies that the state in the horizon should be singular. You know, that if an observer tries to cross the horizon, will be fried, will be killed by the energy of the quantum field. I am not deriving that. I am just telling you the result. I repeat the idea. Initially, we have correlations between stuff inside and stuff outside. If I want to recover, to make all the information to go outside, I have to break the correlations between 1 and 2. And put those correlations between 1 and 3. They have studied that in detail, and they tell you, if you want to do that, then necessarily you will find infinite energy on the quantum field on the horizon. This is what they call a firewall. So the conclusion is that if you want to recover unitarity outside the black hole, then the horizon must be a extremely singular surface. In particular, the energy on the quantum field over there must be divergent. So if a free-falling observer, we can have a horizon here, tries to cross the black hole, will be killed.
So we probably don't have a horizon in this room.
Or to the half firewall. So opponents of this idea say that it is a radical modification of general relativity and quantum field theory to say that something dramatic happens at the horizon. Because, as I said before, the horizon doesn't have anything special. We could have a horizon in this room with arbitrary low curvature. So saying that something dramatic, like a firewall, happens on a surface which has nothing special is a radical modification of our understanding of GR and quantum field theory. This is why many people doesn't support this idea. But our job is to explore many ideas, so you may like it or you may not like it. So for me, it's difficult to believe that something dramatic happens at the horizon. But there's people who believe the other way around. So.
But this should be observable, right? I mean, if something falls in, it should make like a big old burst of energy, right?
It's difficult to make concrete predictions because these are speculations.
And like, I mean, we cannot distinguish between those particles, right? Like here we have assumed to label 1, 2, 3, but actually can we label particles there because they should be all identical.
Right. I mean, they are just the modes that we use to quantize the field. So, but if there are correlations between these modes, the quantum state in a straight class will not be a density matrix because remember that then the formula they wrote for the Hawking thermal density matrix, which before that, the in vacuum, as I said before, is a sum in n of n quanta going inside the black hole to the interior cross n quanta in the out. This will not be true anymore. This will be done by some n prime out and a out. So you will have correlations between out quanta. This is what these guys are saying.
Okay.
But if you want to do that, if these initial correlations have to be translated to out quanta, then something dramatic must happen in the horizon. So if you want to recover unitarity in the straight class at any price, the price is quite high. Because you have to break quantum mechanics or causality. Causality because stuff inside the horizon, information has to go out. Or quantum mechanics if you want to break unitarity. So the price to pay is very high. Any question?
So if anything falls and gets destroyed at horizon, would that not make it visible? Like, somebody else?
But as I said, making predictions about concrete observations.
If something blows up at the horizon.
But the redshift in the horizon is infinite, so you can never see from outside a photon coming out arbitrarily close to the horizon. It will take infinite amount of time. So all that stuff is just unobservable. And a last proposal, just to finish. Singularity resolution. And this is the view, if you ask me what I support, this is the view that I support. And just let me start saying that in the standard formulation of the information loss paradox, one starts with this Penrose diagram that Hawking wrote for us. And I believe there is very strong assumptions implicit in this kind of diagram. In particular, you are accepting that the singularity, r equals 0, acts as a sink of information. So it is able to absorb as much information as you want, and finally completely disappears without leaving any trace. So just let me write it because this is what it is. So one implicitly assumes that the singularity acts as an non-sociable sink of information. Which disappears from the space-time after the evaporation, leaving no trace. No trace. I believe this is an extremely strong assumption. Again, each Hawking quanta reaching here is 100% correlated with quanta going here. So the singularity is just absorbing as much information as you want, and in this picture you say that after some time that disappears, and there is no trace in the space-time. So to me, the problem is here. To me, it is difficult to make statements about what happens with information if you don't tell me what happens here. I think it is almost impossible to clarify the situation unless we clarify what is going on here. Let me put it in an even stronger way. This space-time, this diagram, is not globally hyperbolic. It cannot be foliated via Cauchy surfaces. And we know in general relativity, the classical theory, that if you give me the equation of motion of a scalar field, this equation is hyperbolic. And we know that this hyperbolic equation plus global hyperbolicity of the metric tell us that the initial value problem is well posed. I mean, this is just a more mathematical statement. That if you give me initial data at any Cauchy hypersurface, classically, you will be able to determine uniquely the field at any other time in the space-time. But if this is not true, if this is not true, if the space-time is not globally hyperbolic, then even classically, if you give me a configuration of the field in a Scalate class, I cannot evolve back in time and give you the configuration of the field in straight lines. So I would say that even classically, the evolution in this space-time is not a canonical transformation. It's not a symplectic or Hamiltonian evolution, even classically. So I don't expect that the quantum mechanical evolution to be unitary. Because even at the classical level, the evolution is not Hamiltonian. The space-time is not globally hyperbolic. So all the information in the classical field that goes inside the singularity is lost forever. So I think that even at the classical level, the space-time has problems in it. So if somebody asks me, what do you put the question mark? I would put the question mark in this space-time. So I think this space-time has assumptions, extremely strong assumptions about the singularity. Again, it's acting as a sink of information and then disappears completely. This is where the information loss paradox, in my opinion, arises. So what is the resolution? I don't know. One needs to clarify what happens there. If you ask my bet, what do I bet is going to be the solution? I could write a Penrose diagram, which is not like that. It's something like this. So remember that in the singularities that we find in general relativity, nobody believes that they are real singularities. We don't believe that that nothing in our universe is singular. Remember, the singularity is just an extrapolation of GR in a regime which we don't trust it. But we are extrapolating and then using that crucially in our information loss paradox. That seems to me contradictory. So to me, the information loss paradox seems to be extremely related to what happens with the horizon, with singularity. So imagine that rather than, what is that one?
Only the
So imagine that rather than having a singularity, what you have is some region of the space-time, which is a quantum gravity region, QG, in which the space-time becomes quantum, and the curvature is the Planck scale. It doesn't make sense to talk about a smooth geometry, a smooth space-time. It's just quantum form or whatever you want. So what happens is that you have the star collapsing. The star will produce one of these horizons, which is not an even horizon, because I don't want to enter into details, but it's one of these dynamical horizons. This dynamical horizon will start emitting Hawking radiation. Remember Hawking radiation? I shouldn't do that, because Hawking radiation is something on the sky class, as I have emphasized. There is Hawking partners, which is some quanta going inside. But if this is not a singularity, it's just a quantum gravity region. This stuff can go and reach to the future. So let me write on the top of this diagram the other one. So in the other one, we assume that the space-time is just this region. Maybe I don't see if you see anything. So the orange stuff is the previous space-time. Now I am saying that it is very possible that if the singularity is not a singularity, but is some high curvature regime, the future sky class is much larger than what we believed a priori. We have all this additional region of sky class, which is not in the orange diagram. And in fact, the partners of Hawking radiation could come out in that region in such a way that the sky class is really a Cauchy hypersurface. And if you consider correlations between here and here, the state is a pure state. It's not an X state. I think that is very plausible. That is the solution. But that Hawking quanta go through the quantum gravity phase and arise at late times, or at early times in the extension of a sky class, in such a way that correlations between here and here arise and the state is pure.
So what arises on the more top side of square plus is not like Hawking radiation, where we just kind of, what do I want to say, observe it, but it actually evolves.
Right. It's probably not a thermal state. It's just some quanta that reach there. Maybe they even have zero energy. That is possible. But they keep correlations with this one.
But the Hawking radiation that we talked about in the other classes, we didn't say that evolved through time from the black hole outward. We just say we observed.
Right. Well, it reaches here.
Yeah, but
Right.
for the other ones up there, that actually did evolve, or similarly, we just kind of
I mean,
observed it.
We just observe it. It's the same. That the mode functions associated with them are this one, for the same reason that the mode functions associated with Hawking quanta are this one. Come here. Even though what you measure is here, so it's the same.
Okay.
So thermal, Hawking radiation will be zero here, will become thermal here, and maybe will disappear. But later on, you will have some quanta or just some vacuum fluctuations there, correlated with this quanta here, and making the global state pure in a scribe class. So I would say, if that is true, then you would say that this is incomplete. That scribe class is larger than what you believed a priori, and the correlations are between these guys and these guys. This is where the initial correlations are now. Is that what is going to happen? I don't know. If you ask me to bet, I think this is very plausible. And with this, I just want to emphasize that, in my view, the standard formulation of the information loss paradox makes a crucial assumption and a crucial use of the singularity. That singularity gets all the information and then disappears. It seems to me that is too strong. If you ask my taste, I would say that quantum unitarity will remain in the space-time, and is the resolution of the singularity which will clarify.
That will or would not remain?
Will remain. Unitarity will remain. But is the clarification of the physics in the Planck region what will tell us what happens with the information, and it's very likely that it reappears somewhere else in the space-time. Here we cannot see that because the singularity is just singular. Whatever goes there disappears.
Again, for this we need quantum gravity.
For that you need quantum gravity. Very good. So just to emphasize that people disagree with that, people use the Hawking diagram. I think there are strong hidden assumptions there. What is the real picture? I don't know. Maybe unitarities, yes. But it seems to me that there are other possibilities where I
So the recent paper by Strominger and others, among which proposal does it lie?
It's something else. They have these kinds of diagrams
Yeah.
also, although only implicitly, and they don't say this what I just said here that explicitly. But the main goal of that paper is something else. Is to say that there are other degrees of freedom in the black hole. Remember that the black hole we only have in the horizon mass, angular momentum, and charge. They say that there are other quantum numbers that one can consider and could codify some of the information. But my opinion is that I don't believe that is going to codify the information of the Hawking radiation. That maybe codified other information, like if the black hole is made of grad students or is made of elephants. Maybe those degrees of freedom can distinguish between that. But I don't believe that these new degrees of freedom are going to encode to solve the information loss paradox.
So the horizon disappears after the quantum gravity?
Yes. But there is not an event horizon in the mathematical sense. Because in this space-time, there is no event horizon. Because event horizon, remember, is defined as you go to the future, you trace it back. If you recover the whole space-time, there is no event horizon. There is no event horizon in this space-time. However, you form this kind of trapped surfaces. I don't know if you have studied that before. Sorry?
Idea, dynamic horizons.
This is a dynamic horizon. When you collapse an object, you can, in addition to the event horizon, you can form trapped surfaces, which are surfaces for which light cannot go out, can only go in. And the event horizon is always the limit of all the trapped surfaces. But because the event horizon is so teleological that you need to know the whole space-time, Ashtekar, for instance, proposed this idea of dynamical horizons, which is the same idea of event horizon, but it's quasi-local. You don't need to assume the whole history of the space-time. So it's based on these trapped surfaces. Some like a horizon appears when the star collapses, and after the evaporation process disappears. You don't have black hole anymore. You don't have horizon anymore. I think this is much more physical than event horizon, and this is what I was trying to do here. One of these dynamical horizons which form and then will disappear after the gravitational collapse. In the singularity, the black hole remains because remember that if you go to Sky class and you trace it backward in time, because there is a singularity here, you can never, from Sky class, when you evolve it backward in time, reach on anything inside the horizon. So in this diagram, there is still an event horizon. In this diagram, there is no event horizon. But as I said, we could spend the whole semester discussing those issues. So I just wanted to give you a summary of the main idea, the main proposals. There are all different kinds. Give up unitarity, give up black holes, give up quantum mechanics, give up horizon. There are many things. And I have told you what I believe. And this was my goal. Any question? So with this, I want to finish the chapter finally of Hawking radiation. It's so rich and so deep that that takes time. And I have skipped many things I wanted to say, like energy momentum tensor. One can compute it and see that it's a thermal flux of negative and positive energy. I think even if you do it in 2 dimensions, I think is quite illuminating. And other ways of deriving Hawking radiation that I have worked out in the past using the 2-point function of the field, which I believe is maybe more elegant, but will take me a couple focus on Hawking radiation. But I hope that you appreciate how deep is this, and this is just a consequence of the principles of quantum field theory in coarse spacetimes that we derive a priori. The fact that the vacuum state is not unique, and there is so much freedom in choosing the quantum representation, and the case of dynamical spacetimes, the dynamics tells you what is the natural representation initially and what is the finally, and that gives rise to particle creation, Hawking evaporation, and all these fundamental problems. So this chapter is one of the strongest examples of how useful quantum field theory in coarse spacetimes has been so far. So we have described two examples: Unruh radiation, that an accelerated observer will detect particles, which I believe is something very strong, and Hawking radiation, that black hole evaporation, thermodynamics, information loss paradox. The third example I want to give you is I think at the same level of this or even more, because we can observe that, which is the origin of the cosmic inhomogeneities that we see in the universe. That cosmic structures, galaxies, galaxy cluster, originated from principles of quantum field theory in coarse spacetimes.
Sorry, I did have one question as I think about it. So in principle, if the Hawking radiation were observable, which is kind of a big if, what happened with quantum gravity might also be observable.
If we can see the last stages of evaporation,
And
maybe yes.
The burst later coming from the entanglement or whatever. So the second photon, the diagram.
maybe. Maybe. So that people were very excited with these primordial black holes, but we haven't seen them. As I said, the speculations said that if we live in a multi-dimensional universe, more than 4, maybe black holes can be formed in accelerators, in LHC, because gravity at higher energies is stronger than what we believe. We haven't seen that. In my opinion, the most promising avenue to see Hawking radiation is in these analog models that people take Bose-Einstein condensates and they simulate black holes with sound waves and there are claims that people have seen that. But the temperature is normally so low that you have to see that only indirectly, rather than observing Hawking quanta. You observe density correlations in Bose-Einstein condensates or something else which is related. So it's difficult. But
We talk on that.
right, we have.
But you won't see
We
the
have
quantum
ecology.
gravity there.
Sorry.
You won't see the quantum gravity.
No,
there.
because there the underlying physics is very different. So it's only an analog model.
Right.
So
But-
Related to Manny, like Voltec.
yes. He's from Iceland or Finland.
I just thought he was Russian.
I think he works in Finland. He works on that a lot.
Being foreign. All that.
So I think
Thanks.
it's a very. I wanted to dedicate only half of the class, but as usual. But I appreciate all the questions. And so, do you have any question about this, or I will close the chapter of Hawking radiation?
I have
Right.
maybe a silly question. I've been reading a lot of Voltec and a lot of the other people like Xiaola and Wen who really try to approach the questions of gravity from a condensed matter perspective. And a lot of the arguments they're making, which a lot of people kind of don't know what to think, is that the vacuum, and the space-time vacuum, is actually a very complicated microscopic structure that we can't observe, while things like photons and electrons are emergent phenomena, kind of like a phonon that appears in the Bose-Einstein condensate. We're saying we can't observe the Bose-Einstein condensate, but we can observe the phonon. And they're saying a lot of the strange things happening in gravity may be due to this. Do you think that's kind of a funny sort of argument, or what do you think about that?
I mean, there are many ideas in literature. All these proposals but that is something different. That is quantum gravity. We are doing here quantum fields in a
Well,
quarter space time.
Is the assumption that the space-time vacuum might be just some very strange, complicated
But
substance.
they are talking about the vacuum of gravity, of the
Yes.
space-time itself.
Yes.
We are here talking, this is different from the in vacuum that we are, here the in vacuum is the vacuum of the scalar field living on the space-time.
Mhm.
So the space-time here is classical, and the quantum field is quantum. You have a vacuum for this guy, the in or the out vacuum, whatever you want to consider, but this guy is classical. What they are saying is that, one can also quantize the gravitational field and have a vacuum for the gravitational field. So the question is, many people believe that gravity maybe is an emergent phenomena. It's not fundamental. It's like, like a continuum in a fluid, that there is no really fundamental thing, maybe that phonons, which are only macroscopic excitations and doesn't make sense at the fundamental level. So maybe many people argue that may be also the case of gravity, and therefore doesn't make sense to quantize gravity. It doesn't make sense to talk about quantum gravity. You may believe that I disagree because I work in quantum gravity. So who is right? We don't know. This is the business.
When I was
I believe that that when you have G mu, we know that this must be quantum. So I would find it simply unlikely that this is quantum, but it's not. I don't think that can be compatible. And even if gravity is an emergent phenomenon, we quantize phonons. You can do a quantum theory of phonons. So of course, nobody knows the final answer. So I think all arguments and all discussions are very welcome. And it's a rich field of discussion.
I was reading that there was Shao-Gan 1 specifically was trying to work on some theorem to directly relate what he was doing to quantum gravity in particular. He was working with something called stringnet condensations to say that electrons are actually the ends of one-dimensional strings that exist in this very strange space-time vacuum fluid thing. I don't know, have you heard about any strange theorems like that?
No, I don't know that in particular. There are many things like that, but there are so many that I don't know.
I hardly understand.
I don't know all of them.
Okay, so in this APS meeting, did you get to listen to
Yes.
this 4 or?
Not all these 4, but some of them.
Firewalls.
Firewalls and other ways of modifying quantum field theory to make the correlations arise with the horizon, but not in this plot, of course. In this, so some modification of quantum field theory that make correlations between these two guys. But normally all them assume drastic changes of GR and quantum field theory in a region in which you don't expect that. You don't expect quantum field theory. You expect quantum field theory and gravity to be modified there drastically. Quantum gravity regime, but you don't expect that out of the horizon. So all these ideas, they assume some modification, a strong modification of gravity or quantum field theory in a regime in which we don't expect that. Maybe that is right, but to me it seems implausible. Or it's just it's a more radical assumption. But who knows? We are in a business. This is a question, and nobody knows what the answer is. So it seems to me that one, because the Hawking quanta here is completely entangled with I think and they also think that in order to take these correlations and make the correlation outside, you have to do something drastic. But in my opinion, the problem is clearly here. Okay, so next day I will start. We only have 3 lectures to go.
Oh, really? Yeah.
Oh.
So I will give you a fast summary of quantum fields in Riemann Robertson workshop, which I think will be extremely fast because I could leave that as an exercise because it's quite simple, much simpler than Hawking radiation because everything is very simple. And then inflation, and those who have been in my course cosmology have seen those arguments, how inflation arises. So I will go over that maybe quickly.
When did you take course in cosmology?
Last semester.